Hey everyone, and welcome to section 4.2 on applications with systems of equations. So we're covering this section kind of lightly. I'm really only going to focus on one kind of application, the uniform motion applications. And then we'll look at some more in the next section. So we've already seen these uniform motion applications before in previous sections, using the formula D equals RT. So, alright, we have a river cruise sailing 60 miles downstream for 4 hours, and then took 5 hours sailing upstream to return to the dock. We want to find the speed of the ship in still water, and we want to find the speed of the current. So here's a little diagram. We have the ship going downstream. So when the boat is traveling downstream, the speed of the current and the speed of the boat are going to be added together. They're combined because the boat is going faster than it normally would. But when the boat is going upstream, the current is pushing against the boat. So the boat is going to be going slower upstream than it was downstream. And what we want to figure out is the speed of the ship in still water and the speed of the current, which I've kind of represented with the red-orange arrow and this blue arrow. So we have to name our variables. So I'm going to let S represent the speed of the ship in still water. And similarly, I'm going to let C represent the speed of the current. Alright, next we need an equation that's going to help us out. So let's remember we have our trusty uniform motion formula, D equals RT. So we have this information, the D equals RT for both trip downstream and the trip upstream. Let's write an equation for the trip downstream. So D equals RT. I know what D is, it's 60. I'm going to leave R as R for right now, and we know that T is 4 hours. So let's think about what the R should be. Remember we talked about earlier. So the rate at which the boat is moving down the river is going to be the sum of the speeds of both the ship and the currents. So that would be S plus C. And then let's look at the trip upstream. The distance is the same, but the time and rate are different. So while we're going upstream, since we're fighting against the current, and actually, my arrows are going the wrong way here, huh? There. So when we're going upstream, we're fighting against the current. And that means that I am taking the speed of the ship and I am taking away the speed of the currents. So here's our system. And I'm going to solve this guy by substitution. So I'm going to take that top equation there and solve it for one of the variables. I guess I'll solve it for S. So S is 15 minus C, and we're going to take that expression and we're going to plug it into this second equation in place of S. And then I'm going to simplify and solve for C. So we get that C is equal to 15 over 10, which means that C is 3 over 2 miles per hour. Okay, to get S, we're going to look at the expression that we substituted into the second equation. S is equal to 15 minus 3 over 2. And there we have that S is equal to 27 over 2 miles per hour. So let's do a quick check. Okay, so the answers check out. Now all we need to do is write a sentence. Alright, now being a somewhat real-life application, I converted the numbers to decimals, although it's not strictly speaking necessary. So there we have it. The boat was traveling 13.5 miles per hour in still water, and the speed of the current was 1.5 miles per hour. So another example, this one is really just the same as the previous one. Even though you're talking about something in the sky, we still have this idea of traveling with a current and against a current. So we have a small jet flying 1,325 miles in 5 hours with a tailwind, but only 1,035 miles in 5 hours with a headwind. We want to find the speed of the jet in still air and the wind speed. So I'm going to draw a picture. Okay, so we have the air current there represented with the blue arrows. So just like before, when we have a tailwind, the two velocities are helping each other. And when we have a headwind, they are fighting against each other. So this is really working the exact same way as the previous example, except the information that we have is slightly different. In this example, the time is the same, but the distance is different. Now I need to name these variables. So let's let J be the speed of the jet in still air. And we'll let W be the speed of the wind. Right, so as before, we're going to have two equations, one with the tailwind and one with the headwind. So we have 5 hours times our rate, which is going to be J plus W, and that's equal to 1,325. Then we have the headwind, which is again 5 hours times J minus W now. So let's simplify those. And there's our system. Now, by the looks of things, this system is a prime candidate for solving by elimination, because the W coefficients are already opposites. So let's add the two equations together. So we get that 10J is equal to 2,360, or that J is equal to 236 miles per hour. From here, we want to figure out what W is. So let's use one of the equations. And we get that W is equal to 29 miles per hour. So let's do our quick check. Okay, everything checks out. Now let's just write a sentence. And that's our solution for that problem. Alright, so here's a diagram of this situation. Basically, Suoma leaves 15 minutes earlier than Irie does, and is able to put 15 minutes worth of distance between them before Irie starts moving. Because Irie is moving faster than Suoma, eventually she'll catch up. But we want to know how long is that going to take. And to do that, we're also going to need to know how far they've traveled away from their mom's house. So we got to name our variables. Let's do that. Alright, so since Irie is traveling 42 miles per hour, we know that the rate times the time gives us the distance, so 42 times t, which is the time until she catches up, equals d, the distance from the mom's house when Irie catches up. And then we also want to write an expression for Suoma's distance. It's the same distance and the same time in both equations, but keep in mind that Suoma had a 15-minute head start. So she already traveled 15 minutes worth of distance, which 15 minutes is equal to a quarter of an hour. So how far did she go in 15 minutes? Well, that would be 36 times 0.25, which would be 9 miles. So to properly calculate the distance from their mom's house when they meet up, we have to add in that 9 miles that Suoma had already traveled. Okay, now, this is pretty prime territory for substitution again, because both equations are in terms of the same variable. So I can just set these two guys equal to each other. So t equals 3 over 2, or 1.5 hours. And let's see, does that check out? So indeed, the two are equal. Finally, we'll write our sentence. There we have it. It takes 1.5 hours for Irie to catch up to Suoma. And I think I'm going to call it good here on uniform motion. Next up, we'll look at some mixture problems.